Good morning everyone. In this video, we are going to analyze a frame structure by using stiffness method. This is me Dilruba KM, and again I have taken an example from previous year university examination. Okay, so the question is, analyze the rigid frame loaded as shown in figure using stiffness method. This question was asked in 2018 December for 7th semester BTech degree examination. Okay, so let us see the steps for analyzing this structure. There are 10 steps to analyze a frame structure by using stiffness method, and the first step is to calculate kinematic indeterminacy. Then we will assign system coordinates according to the degrees of freedom, and element coordinates will be assigned in third step for each element of the frame. After that, we have to calculate the fixed end moments, and then we will form a displacement transformation matrix. Then we have the equation, or we have element stiffness matrix, that is EI by L in 4224. And the seventh step, we will develop a stiffness matrix with equation K is equal to A transpose K star A, and develop force matrix in the eighth step. And at ninth step, we have to develop displacement matrix, and finally we will calculate the element forces. Okay, so these are the 10 steps that we should follow in order to analyze a frame structure by using stiffness method. So let us see how can we do this. So our figure was like this, and in order to calculate degrees of freedom or kinematic indeterminacy, we have an equation for frame structure. dk is equal to 3j minus m plus c, where j is number of joints, m is the number of members, c number of constraints, and in this figure it is clear that number of joints are 1, 2, 3 and 4. So j is 4, number of members are 1, 2 and 3. So we have 3 members, and constraints, since both are fixed ends, the constraints are 3 plus 3 is equal to 6. So the degrees of freedom or kinematic indeterminacy is 3 times j minus m plus c. Okay, so 3 times 4 minus 3 plus 6, which is equal to 4. So we have 3 degrees of freedom. Since this is a sway structure, there is no degrees of freedom that is neglected. So we have 3 degrees of freedom, and we will assign system coordinates according to the degrees of freedom. Here we have one system coordinate, and second one, third one. Okay, so these are the system coordinates that we are assigning to this structure. Third step is to assign element coordinates. For every element, there will be 2 element coordinates: 1 star, 2 star, 3 star, 4 star, 5 star and 6 star. So these are the element coordinates that we have to assign. So there are 6 element coordinates. The fourth step is to calculate fixed end moment, and we know the equations for calculation of fixed end moment. That is, when a concentrated load is acting at the midpoint of this beam, it will be minus WL by 8 at this end and plus WL by 8 at this end. So FEM AB, let me name it as A, B, C and D. So FEM AB is minus 27, FEM BA is plus 27, FEM BC is again 96 kilonewton is also acting at the midpoint of BC. So FEM BC is minus 72 and CB is plus 72. And in the case of CD element, there is no load acting on it. So the fixed end moments are 0 for CD and DC. So we have all these fixed end moments. Now we will move to the step number 5, that is to form displacement transformation matrix. And we know in order to obtain displacement transformation matrix, we have to apply unit displacement in the direction of each system coordinates separately. So for first system coordinate, that is, I'm naming it 1, 2, and 3. First system, second system coordinate, and third system coordinate. We have to find out the displacement transformation matrix for each element coordinates 1 star, 2 star, 3 star, 4 star, 5 star, and 6 star. So we have this matrix like this for first system coordinate, second system coordinate, and third system coordinate. Corresponding displacement, internal member deformation occur at each element coordinates 1 star to 6 star. Okay, so when I apply unit displacement in the direction of the first system coordinate, keeping zero displacement on second and third system coordinates, so we have only unit displacement occur in the direction of first system coordinate. So the 1 star will become minus 1 by length of AB, which is 6 meter, BC is 6 meter, and DC is 7.5 meter. So length of AP minus 1 by AB's length is 6, and 2 star also it will be minus 1 by length of AB, that is 6. And for 3 star and 4 star, since the unit displacement is occurring in this direction, and this unit displacement will give it only an axial deformation, but in the case of matrix method we are neglecting the axial deformation, we are not considering the axial deformation. So the deformation, internal member deformation occur in 3 star and 4 star are taken as 0. So there won't be any member deformation occur due to first system coordinate. And for 5 star it will be minus 1 by 7.5, and for 6 star also it is 1 minus 1 by 7.5. So in first case we have entered the values of elements on the displacement transformation matrix when we apply unit displacement in the direction of first system coordinate. Now we are moving to the second system coordinate, that is a moment. So we are applying a unit moment in the direction of second system coordinate, keeping displacement in first and third system coordinate at 0. So now we have only second system coordinate with unit displacement. So since the second system coordinate is acting at point B, only 2 star and 3 star will have unit displacement due to second system coordinate. All other element coordinates will have zero displacement. Okay, so we will write when I apply unit displacement in second system coordinate, 1 star will have value 0, 2 star, 3 star both are at B, so they will have values 1, and 4 star, 5 star, 6 star all have values 0. Now I am going to apply unit displacement in the direction of third system coordinate, that is also a moment which is acting at C. So only 4 and 5 have unit displacement. All other element coordinates will have 0 unit displacement. Okay, 0 displacement. So let us see what will be the values. For 1 star it will be 0, 2 star 0, 3 star 0, and 4 star and 5 star both are at C, so they will have unit displacement. At 6 star it's again 0. So this is how we develop displacement transformation matrix. When you are given a horizontal displacement, only the vertical members will get values of displacement transformation matrix, that will be minus 1 by length of that particular member. Okay, so this is how to develop displacement transformation matrix. So this is our displacement transformation matrix. I just write it down in terms of decimals. Now we may need A transpose, so I am writing down the A transpose over here. And the sixth step is to form element stiffness matrix. So in order to form element stiffness matrix, we have equation K star is equal to I by L 4, 2, 2, 4. So for AB, length is 6. So we are applying the value EI into 4224 divided by 6. It will give you the value. And for BC also the length is 6. So it have same element stiffness matrix. And for CD it is 7.5. Length of the CD is 7.5. So the element stiffness matrix is 0.533, 0.267, 0.267 and 0.533. So these are the values of element stiffness matrix. Now I keep all these element stiffness matrix of each elements, each members of the frame diagonally and form the element stiffness matrix for the structure. So it will be like this. So we have element stiffness matrix for the structure. Okay. I have kept all this element stiffness matrix of each members in diagonally, and we will get a 6 by 6 matrix. Now moving to 7th step to develop stiffness matrix, we have the equation stiffness matrix is equal to transpose of displacement transformation matrix into element stiffness matrix of the structure into displacement transformation matrix. For that we just have to multiply these three matrices and we will get the value as 0.056 minus 0.167 minus 0.106 minus 0.167 1.334 0.33 minus 0.106 0.333 and 1.2. And we are using K inverse in next step. So in the step number 9, so in order to calculate displacement matrix, we may need K inverse. So I have just calculated K inverse. This can be done using scientific calculator. So it's very easy to obtain K inverse. And the step number 8, we have to develop force matrix. So force matrix is nothing but the value of external force in the direction of each system coordinate. So we have first system coordinate in this direction, second system coordinate and third system coordinate. Both are rotations in clockwise direction. So now we have to assign or we have to find out the values of external force in first, second and third system coordinate. For that we are taking the structure again with external loadings. We have 36 kilonewton and 96 kilonewton in between AB and BC. Okay, so in order to find out the value of first system coordinate, I am taking AB alone. Okay, AB, I have taken AB, and we have found out the fixed end moment of AB in step number 4. That was minus 27 here and plus 27 here. Okay, so plus value is positive value is taken for clockwise moment and negative value for anti-clockwise moment, and we have 36 kilonewton. So I just keep this AB in horizontal format. Okay, so our first system coordinate will be like this. Okay, so I am naming it as RB. Okay, RB. We have 3 meter, 3 meter. Now I just have to find out the moment at A. Since at A we have fixed end moment, fixed support, we know the moment at A will be 0. So moment at A will be 0. So I am calculating the moment at A with these all values. So at A we have a moment that is minus 27 plus we have 36 into 3 plus we have another plus 27 and then again RB times 6, which is also coming around as a clockwise moment. Therefore I have taken it as positive. Only minus 27 is negative So we have minus 27 plus 36 into 3 plus 27 plus RB into 6 is equal to 0. So minus 27 and plus 27 get cancelled. So RB into 6 is equal to minus 36 into 3. When I take this 36 into 3 into right hand side, it will become minus 36 into 3, which is, so RB is equal to minus 36 into 3 divided by 6, which is equal to minus 18. So value for first system coordinate is minus 18. Okay, now we have value for first system coordinate, it's minus 18. Now we have to calculate the second system coordinate. And in second system coordinate, we have already, it is second system coordinate is a moment, right? Therefore, in order to calculate second system coordinate, we can make use of fixed end moments at B, that is at BA and BC. So both are acting at B. So FEM BA plus FEM BC will give you the second system coordinates value. So FEM-BA is 27 and FEM-BC is minus 72. So the value will become minus 45 kilonewton meter. Okay. So this is the value, external moment value for second system coordinate. And similarly for third system coordinate, we have fixed end moment at C, that is fixed end moment at CB plus fixed end moment at CD. Since the value of CD is 0, so we are just taking fixed end moment at CB, that is 672 kilonewton meter. So the values for force matrix is minus 18, minus 45 and plus 72. So this is the force matrix we have developed using our structure. Okay. So we may need fixed end moment of each ends that we have calculated this fixed end moments in step number 4. So you can just take it out from there. So it is very easy to calculate the force matrix, I guess. So let us move to the second last step, that is step number 9, displacement matrix. So we have the equation minus K inverse P. We have K inverse and P. So we are just substituting these values, minus K inverse P. So the value, when you multiply this K inverse and P, you will get the value as minus 600.21, minus 118.8 and 39.96. So these are the displacement matrix, that is displacement occur in this structure. Okay. And the final step is to calculate element forces. We have the equation Q is equal to K star. K star is the element stiffness matrix of the structure, and displacement transformation matrix and displacement matrix. So we are just multiplying all these matrices and you will get the answer as 60.67, 20.96, minus 65.93, minus 12.91, 84.92 and 74.2.